Hi, I'm Chris Burke, and I'm in Tim Atherton's group at Tufts University. The work I'm presenting here is part of a larger project in which we're trying to understand the phenomenon of arrested coalescence. Arrested coalescence occurs in emulsions when two droplets start to coalesce, but because of the presence of colloidal particles on the surface, this coalescence is arrested, and you end up with structures with interesting shapes like what you see on the left here. And so the colloidal particles on the surface become close packed, and we're interested in looking at how the variation in curvature along the surface influences defects in this packing. And so we do this by running simulations to create packings of hard spheres on spheroidal surfaces. When we run a simulation, we specify the aspect ratio of the spheroid, and we specify the number of particles on the surface. And we have an algorithm which moves the particles around and inflates them until they're close packed. So the first thing we look at is how defects couple to curvature. We do this by splitting the spheroids into equal area sections, as is illustrated here, and we count the number of defects in each section. And so we sum the results over many configurations, including configurations of different particle number. So displayed here are the results for varying aspect ratio. You can see that for a sphere, the distribution is pretty much constant over the surface of the sphere. But for spheroids, you can see that defects tend to form much more often towards the poles where the curvature is higher, and there's less around the equator where there's not much Gaussian curvature. And so this is pretty much what we expect. And from here, we're trying to find a way to a more quantitative way to characterize how defects couple to the curvature. So next, we're interested in what we call the scar transition. So a scar is these chains of defects that you can see in the configuration here. And so some studies have been done on this before, looking at packings of particles onto a spherical surface. And it's seen that at low particle numbers, scars don't form. You just have a minimum number of required defects. But for higher particle numbers, you do see scars start to form. And as you increase the particle number from low particle numbers, there's a critical particle number at which these scars start to form, and we call this a scar transition. So in our simulations on spherical surfaces, we see the same thing, but on spheroids, this scar transition is softened. And for high enough aspect ratios, we don't see any scar transition at all. And so it's interesting to point out that in the previous results, the scar transition happened at 400 particles, but in our simulations, it happens at only around 100 particles. And so we want to try to figure out what's causing this difference, and we think what it most likely is that we're using hard spheres, whereas the previous work has looked at soft repulsive particles. And so finally, we're interested in looking for symmetric packings. So on spheres, you can find configurations that have icosahedral symmetry. And so we're interested in finding configurations on spheroids with different symmetries to maybe inspire the design of self-assembling configurations with these different symmetries. What I'm showing here is the number of symmetries that configurations have for varying aspect ratio and particle number. We have a metric which measures how symmetric a configuration is under a given transformation. And so we can look at all the transformations of the spheroidal symmetry group, d infinity h, and count how many of them leave a configuration symmetric. So the bottom chart, here we are relaxing the requirements for what we count as symmetric, and we can see some striking patterns. So we're interested in finding out what causes these patterns, and we also want to take the almost symmetric configurations, and loosely speaking, we want to massage them into more symmetric configurations. And finally, we're also interested in characterizing which specific symmetry groups these configurations lie in. Thanks.